Good afternoon, everyone. I'm Eric Anderson. I'm a librarian with Central Rappahannock Regional Library, and I'm very pleased to introduce Jon Bachman, a lifelong educator, naturalist, and paleontologist. Today, he's going to be talking to you about some very interesting subjects at the Appalachian Amazon. And I'll go ahead and let you get started, Jon.
All right. Hey, well, thanks a lot, Eric. I appreciate it.
Of course.
An Appalachian Amazon, that was I stole that title from an article that I read, and I thought, my goodness, what a great juxtaposition of names and stuff. But this is about an event that occurred on Earth that affected us here in the Fredericksburg, Stafford, Spotsylvania area 56 million years ago. And the more I got into it, the more interesting it became, because as you will see, there's a lot of lessons that we can learn for what happened 55.6.8 million years ago. Let's go to the next slide. So I'm going to read these slides, pause and check out the pictures, kind of get into the feeling. Already you see that this first slide says the configuration of oceans and continents were different 55 million years ago. So, boom, we go to look at the East Coast, right? And we can see that there's a number of unique changes. Okay, so the world was different. Next slide. And this simply shows you where in the geological calendar these events are taking place. And you'll notice the little arrow is pointing between what is called the Paleocene and the Eocene epochs. Next slide. Well, the Fredericksburg area was in the bullseye for a global climate episode. And this event is now being intensely studied by geologists and paleontologists because of the recent steady increases of carbon dioxide levels in our atmosphere. Next slide. Well, 55 million years ago, what would become coastal Virginia was an Amazonian-like world of jungles, heat, humidity, and torrential rains. Next slide. This steaming world would get even hotter at the end of the Paleocene epoch, 55.8 million years ago. Okay. Next slide. About 55.8 million years ago, trillions of tons of carbon dioxide were rapidly released into the atmosphere. This is the Paleocene-Eocene Thermal Maximum, or the PETM, and it had begun. Next slide. What researchers have learned of that time and the effects of the PETM may have a profound impact on our lives. In 1991, paleoceanographers J.P. Kennett and L.D. Stott were studying marine sediment cores from Antarctica. The cores were dated to the end of the Paleocene epoch and the earliest Eocene epoch. Next slide. What they discovered was that during the Paleocene-Eocene thermal maximum, a significant portion of benthic foraminiferans, those one-celled animals that live on the seafloor, died out, with estimates suggesting that 35 to 50% of all the species within that group went extinct due to the drastic environmental changes caused by this event. Okay, next. And that little peak there, that arrow at the top, shows where this event happened. This event is now referred to as the PETM. It shows you on two there. Shows you the two blips on the top chart there of extreme temperatures, and also shows you in this swirly geological timeline approximately where it is again in the geological record. Next slide. What geological event could have caused this so rapid and an increase in global temperatures to happen so quickly? What's going on? Next slide. So what are the characteristics of this PETM? I mean, what's going on here? Next slide. Well, during this time period, there was a sudden spike in the average global temperature. The average global temperature, okay? The global average temperature became 88.9 degrees Fahrenheit, almost 90 degrees. That's the average temperature of the planet. 90 degrees, average. Just to give you a comparison, back in February, or here in February of 2025, the average global temperature is 59 degrees. So you can see that what they found in the research, it was a drastic jump in average temperatures globally. Crazy. Next slide. At the beginning of this time period, the PETM, this is nuts. Between 2,300 and 12,000 petagrams. I had never heard of what a petagram was. Well, a petagram is equal to 1 trillion metric tons of carbon dioxide. Now that's one petagram is a trillion metric tons. Can you imagine 12 million tons, or excuse me, 12,000 tons, metric tons, of petagrams? This is a phenomenal increase. Next slide. Well, this is probably due, they now figure, researchers figure, from a combination of methane hydrates. We'll see what those are in a little bit. Melted permafrost, I think most of us have some idea of that, volcanic activity occurring over a geologically brief time of only a few, I know it's like we live 80, 90 years, but geologically speaking, 3 to 20,000 years is nothing geologically. So this was like, boom, quick, instantaneous almost. Next slide. All occurring within a geologically short period of time, making it a key analog for what's going on now. And I want you guys to file that away, because this whole PETM thing is an analog to what scientists are now unraveling as the global warming of our planet. Next slide. During this PETM, ocean acidification was extremely serious, now causing widespread disruptions in marine ecosystems, significant extinction events among deep sea organisms. Next slide. Well, ocean acidification is the process where the ocean becomes more acidic due to the absorption of carbon dioxide from the atmosphere, causing a decrease in the pH levels of seawater. Now, don't get lost in the chemistry here. Ocean acidification simply means the oceans were becoming more acid, and this was tilting the pH level. Next slide. When the pH level of seawater decreases, the availability of carbonate ions needed for marine organisms to build shells and skeletons is reduced. The potential causes damage to creatures like corals, oysters, plankton, and disrupts entire maritime or marine ecosystems. Now, again, it's the carbon dioxide that's being absorbed by the oceans, which are tilting the pH apparently, and this is then impacting the lifestyles of these marine organisms, many of which we have to have. Next slide. Significant die-offs amongst deep-sea benthic organisms occurred, particularly deep-sea foraminifera. This was due to the ocean acidification, as I mentioned. Next slide. And there were changes in the plant communities and animal migrations due to a warmer climate. So the global temperature of the Earth skyrockets. Ocean acidification takes place. Changes on land immediately start taking place. Especially animal migrations and plant communities are affected. Again, not instantaneously, but in a geological sense, a few thousand years. These are huge changes. Next slide. Research indicates rises in sea level due to thermal expansion of oceans caused by the warming. Oh, so when it warms up, the ocean levels change. Next slide. Studying the PETM provides valuable insights into potential impacts of rapid climate change on Earth's ecosystems. Rapid change, including the effects of ocean, as here we go again, acidification, and large-scale species extinctions. So this is serious stuff, guys. Next slide. The ocean is about 30% more acidic today than it was before the Industrial Revolution. Now that's crazy. The ocean is 30% more acidic. To address ocean acidification, scientists call for greater attention to the global carbon emissions crisis. Well, I mean, it's kind of easy to tell whether the ocean's more acidic. And so 30% more acidic generally. Okay, next slide. According to current scientific estimates, if global warming continues at its current rate, a significant portion of animal species could face extinction by mid-century. And some projections suggesting that up to 1/3 of all species could be at risk of extinction by 2050. That's how serious it is. Next slide. Hard evidence indicating a global warming includes a consistent rise in global average temperatures. Remember that early slide. Increasing ocean heat content. Great. Shrinking glaciers and ice sheets, rising sea levels, decreasing Arctic sea ice, earlier spring blooms, changes in animal migration patterns, and an increase in extreme weather events. Any of that ring a bell, guys? Next slide. Well, geological ages are defined by major geological events, such as mass extinctions, the appearance of or disappearance of life forms, and major geological events. The PETM, this Appalachian-Amazon event, was a major geological event. Next slide. Scientists are using this as a proxy for what might happen on Earth. Now, take a moment, just eyeball that a little bit. Purple, cold, green, temperate, that's like us. Arid, makes, tropical, okay. Check with pre-PETM, and then what happened during this time period. Well, you can see that there were some drastic changes on a global scale. Next slide. How is the PETM being studied? I mean, how are we learning about this? By the way, those are fossil Eocene plant fossils from Wyoming. And they do show, and I selected that slide because these different paleobotanical communities were experiencing high stress during this time too. Next slide. Upon further analyzing of their core samples, Scott and Kennett found an unexpected pattern in the carbon-12 and carbon-13 ratios, indicating a past environmental change not seen elsewhere in the geological record. So this is important, guys. This is what research does. These two guys were studying core samples and ran against some dramatic evidence that showed global changes happening over a very short period of time. Next slide. Their research revealed this event was a period of rapid global warming and oceanographic changes, we've been talking about that caused one of the largest deep sea foraminifera extinctions in the past, ready, 90 million years. Now, 90 million years, 66 million years ago, the dinosaurs went extinct. Okay, so this is big time changes. Next slide. Foraminifera, and I've been bringing that up, are like little timekeepers of the Earth's environmental changes, and they are particularly valuable for identifying past mass extinctions. Okay, so they line up, when this bunch of foraminifera disappear, what else was happening in their communities, so to speak, as far as temperature and salinity and all the different variables that impact the lives of these little guys. Next slide. These timekeepers build shells throughout their lives and are highly sensitive to environmental conditions. Oh, great. They can be used to identify specific geological time periods due to their rapid evolution and short lifespans. That's why they're so valuable in analyzing changes in the life of these of the oceans, so to speak, and also in the geological record and fossils. They have short lifespans, and they can be the markers between them are easily recognizable. Next slide. Research into the carbon-13 and carbon-12 ratio is crucial for studying this PETM because it acts as a key indicator of the source. And this is, so it isn't just like the characteristics of the ocean, but the indicator of the source of where this carbon is coming from. Next slide. These carbon isotope ratio differences are often found in marine sediments, okay, and can indicate a major disruption in the global carbon cycle, potentially linked to climate change, mass extinctions, or other large-scale environmental events. So you can see how this is coming together to point the finger at what's going on now. Next slide. Different carbon isotopes, particularly carbon-12, carbon-13, and carbon-14, are crucial for scientific research because they allow scientists to trace the movement of carbon through the ecosystems, reconstructing past environments and determining the age of organic materials. Now, when was the last time you thought of the carbon cycle? Maybe never, but it is absolutely vital to understanding the dynamics of our planet, And so what this is showing is that it was out of whack. It was this whole carbon cycle, and the ratios are pointing to more global problems and changes. Not only then, I dare say now. Next slide. And this is nuts. Also studied are the effects of something called methane hydrates. Well, check the picture out. Lower right-hand side shows blobs of this stuff as it is at the deepest part of the ocean. These are formed. That white stuff there is methane hydrates. It'll tell you in the next slide, and you could set it on fire. My God, it is much more combustible than many elements, many compounds. Next slide. Okay, here we go. Methane hydrates are crystalline solids, okay, formed when methane gas molecules get trapped within a cage-like structure of water molecules. This essentially creates an ice-like substance that forms under high pressures and low temperatures, bottom of the ocean, typically found beneath the seabed, okay, or in permafrost. That ring a bell from earlier. And they are considered a potential energy source due to the large amounts of methane they store. In addition, their release could contribute to climate change again, and as methane is more potent greenhouse than carbon dioxide. So if you release this stuff, it has effects. Next slide. Scientists study mammal teeth from this time period, since the size and characteristics of these teeth can also act as a proxy for the body size of the animals. Oh, they got smaller. The teeth reveal important insights into the impact of climate change on ecosystems and evolutionary adaptations. I know we don't talk about this too much, but here's the proof. Animals got smaller. Mammals. Next slide. Researchers are also studying the effects of soils, increased seasonal fluctuations in water tables, increased physical weathering, increased chemical weatherings, poor organic matter, decreased soil organic carbon. All of those probably never come up in conversations around the dinner table. But scientists who are hip to trying to figure out the changes on our planet see these as indicators. I mean, this is going on here. So when they're studying the PETM, they're also noticing these changes. Next slide. Inspired by Kennett and Scott's discoveries, teams of scientists are now examining this Paleocene-Eocene boundary, between these two ages, the terrestrial record, and found some dramatic short-term shifts in the environment. What is going on? Next slide. All the evidence, okay, points to a very rapid period of intense global warming. I think you got that. That started and stopped almost instantly. Next slide. The high latitude Arctic may have been as warm as 73 degrees. That's an average, comparable to modern subtropical and warm temperate seas. This guy is standing, leaning on a trunk of a tree that grew. That's the Arctic, guys. And at one time, because of this PETM, again, temperatures skyrocketed. And you can see how fast life adapted. Boom. You have temperate, semi-tropical and tropical plants growing as high as latitudes is Labrador or Newfoundland. And this obviously shows a picture of stuff that was growing in much higher latitudes. Next slide. This discovery marked the first time scientists could identify a past global warming event of such magnitude and rapid onset, providing valuable insights into the impacts of rapid climate change, i.e. now, guys. Next slide. The PETM arguably represents our best analog from which to understand what's going on now with the global warming and how carbon cycles operate in a greenhouse world. Next slide. What was happening in Virginia, and in particularly Stafford County, Virginia. Oh my God. Next slide. What was Virginia like? What was the Virginia world like 55 million years ago at this dramatic point in Earth's geological history? Okay, what was it like here? Next slide. The state was mostly underwater along the coast, while the central and western regions of the state were rolling hills and lowlands. Okay. Next slide. Coastal Virginia during the late Paleocene epoch experienced two seasons, one hot, humid, and rainy, and the other drought with limited rainfall. So a two-season environment. Okay. This was, again, right there before this PETM hit. Next slide. 55 million years ago, during the last of the Paleocene epoch, Virginia experienced a warm climate. Even deep ocean waters were relatively warm during this epoch. So the planet was warmer than it is now, but not like it's going to get. Next slide. The global average temperature for us here was about 75 to 77 degrees with tropical and subtropical conditions. And it was temperate again at the poles. Very little ice and quote unquote snow. So that was then. Next slide. Globally, mammals became larger and more diverse, including extinct placental mammals, large herbivores, and the first known primates. Hey, our ancestors. In fact, there's one sitting on the branch right there. Many modern plant species also appeared, such as palms and cacti. So the world was warming. Animal life was adapting and evolutionarily expanding into different special realms, so to speak. So that was 55 million years ago. Boom. Next slide. Marine invertebrates such as mollusks and plankton expanded. Sharks and teleost fish, that's regular fish, became more common. Bony fishes dominated the sea. Okay. Next slide, please. The continents continued to drift toward their current positions. Africa was heading north toward Europe, closing the Tethys Ocean. India began its migration to Asia, which would lead to the formation of the Himalayas. Next slide. Then, guess what happened? The PETM changed everything for a while. Next slide. As temperatures rose and precipitation increased, erosion, again, this is looking at us around here, erosion intensified. Next slide. The PTM monsoonal rains deluged ancient Stafford County. Next slide. And when you have all of that precipitation, you have increased erosion, which drives chemical and weathering changes. I know we don't think about it, but that's what's going on around us all the time. And if you're increasing the precipitation and the temperature, you're going to have these reactions increase. Next slide. The I was tilted on the side there. Anyway, you can tilt your head there a little bit, guys. You can see that dark area there. The geological analysis of the Paleocene deposits in Stafford County reflect these conditions. And I'll explain that in a minute. I wonder why they did that. Next slide. A signature of the PETM in Virginia are what are known as hard beds that have been produced by a combination of rising temperatures and increased mineral precipitation. Okay, so when you have more water, you're going to have more precipitation, more chemical reactions, and you'll see what happens here. Next slide. Guess what? Locally, we have opals. As a result, potch, P-O-T-C-H, also known as common opals, are found in the Paleocene sediments in Stafford County, Virginia. That's pretty crazy. We have our own set of opals. They're not the fiery kind of Australian opals. They're mostly blue, green, and red. Next slide. Now, these potch or common opals tell the story of the PETM because you got increased water running through the earth, picking up silica from the sandstone. You got the silica-rich water filling cracks caused by little faults and decomposing fossils. And as a result, as it evaporates, the water, it leaves behind the silica deposits. The silica-rich water fills cracks, okay? As the water evaporates, it leaves behind the silica, and over time, this silica deposits form common opals. So, increased temperature, increased precipitation, increases the mineral characteristics and reactions, and we have opals here in Virginia, in Stafford County. Next slide. And another thing that is the result of this PTM here locally is deposits of what is called kaolinite. Kaolinite, next slide, please, is a soft, earthy, usually white mineral produced by chemical weathering of aluminum silicate minerals like feldspar. Don't sweat all that stuff. Chemical weathering is the key element there. This is the product of erosion, more rainfall, etc. Was deposited forming a layer known as the Marlborough clay, which is kind of mysterious for geologists and paleontologists. Where did it come from? Why is it here? Well, it's probably the result of PETM. And we got it. Next slide. The mineral indicates a rapid and intense rise in atmospheric heat and erosion caused by tropical rainfall. So as it got hotter, it rained more. And more intense mineral reactions occurred. Next slide. Locally, the Marlborough clay is considered unusual due to its exceptional high concentrations, you ready for this? Magnetic nanoparticles. This means that the magnetic poles in these little, in the atomic in the structure of this clay are aligned with one another, pointing in the same direction. This is likely resulting from a unique environmental event, the PTEM, during its formation, possibly related to the PETM period of rapid climate change. This high magnetization makes it a valuable tool for studying past environmental conditions. So you have a number of scientific insights that are coming together to draw the conclusion that this PETM is significant and is the result of these spikes in tremendous amounts of carbon dioxide released into the atmosphere. Next slide. Studying the Paleocene-Eocene thermal maxima teaches humanity that rapid carbon emissions can lead to dramatic and potentially irreversible climatic conditions. This highlights the importance of taking action to mitigate greenhouse emissions today to avoid similar drastic future consequences. Essentially, it serves as a cautionary tale about the potential dangers of unchecked global warming. Next slide. and we got a lot to learn, guys. So this is I think that's the last slide in the presentation. Yeah, we have a lot to learn, and it all started with those guys in Antarctica pulling up some cores that about the Paleocene-Eocene contact, 55 million years ago, and then digging deeper into it, literally, no pun intended, but finding out there are more causes for this and how rapidly it happened, and it as rapidly decreased as it had happened. So it started rapidly, ended rapidly, and has much to teach us. And I think that's it. Next slide. There you go.
All right. Thank you so much, John. That was fascinating.
So now you know all about the PETM.
And thank you, everybody, for viewing. Have a great day.
Hey,